The original branch engine was, in a sense, a fairly conventional oscillator. While external features were unusual, to say the least, the joint axes adhered reasonably well to the geometric constraints characteristic of a typical oscillator. In spite of the wood-on-wood joints and seat-of-the-pants construction, it did run and behaved in the same general way as better engines, just with reduced performance. But the original goal was to test the limits, and it fell short of this goal. I'd made the assumption that the joint axes perpendicularity and in-plane constraints were mandatory for an engine to even run. This assumption violated an important design rule: verify all assumptions. So let's examine those assumptions with a more open mind. I was tempted to, again, just start whittling wood, but I realized that I didn't have a clear configuration in mind. Time for some CAD modeling. Here's a model similar to the original branch engine. In the side view, the rotational and sliding axes are perpendicular and they lie on a vertical plane in the top view. The model behaves as expected. Note that the mouse cursor grabs a component and moves the entire mechanism as though we're moving it by hand. Since the goal was to relax the geometric constraints, I just threw together something that looked a little like the original branch engine, but with axes skewed at random angles, pushing this well beyond my level of comfort. The only relationship that seemed mandatory was the perpendicularity of the pivot shaft to valve faces, since an illustration in the original branch engine video demonstrated that significant error here would produce valve leakage. Beyond that, everything was fair game. Even though it seemed clear that it wouldn't work, the rod end bearing was initially constructed as a sleeve, mating with the skewed crank in one position. The model did assemble, but checking the CAD model behavior, the mechanism was frozen. The cursor won't move the mechanism. But suppressing the rod end joint, the remainder of the mechanism moves as expected, without closed-loop constraints. The rod end bearing seemed a good place to make changes. Clearly the rod end joint must relax some degrees of freedom, so let's try a spherical joint at the rod end, fixing it axially on the crank pin. It works, but things are a little strange. The crankshaft has to slide axially for a kinematic solution through an entire revolution. Imagine the vibration of an engine with a heavy flywheel pumping back and forth like this, not to mention the added friction loss in the axial bearing. Also note that there's some interference at the spherical joint. So let's fix the crankshaft axially, but add a secondary crankshaft that's splined to the back portion. This model also adds a commercial ball joint rod end to replace the spherical constraint. Again, this works, but it's a little complicated, and the large moment on the spline joint would result in significant friction losses. Okay, let's try the obvious and let the ball joint slide on the crank pin. It works, and this seems the preferable degree of freedom to relax to minimize friction losses. We need a fairly long crank pin, but that seems okay if it's strong enough to tolerate the bending moment. The kinematics work, and that at least suggests that an engine with dramatically relaxed geometric constraints might run. But kinematic solutions don't include forces, and particularly friction forces, the bane of engines that don't run well or don't run at all. So let's try the real thing. Back to the maple branch. Again, this was made without drawings or dimensions, just glancing at the CAD model for rough guidance, and using the same general construction approach illustrated in the original branch engine video. Being lazy, I rejected making a ball and socket of wood, opting for a short, sloppy rod end bearing surface that seemed to have roughly the freedom that might be needed. The joint axes seem almost absurdly skewed, and I worried that I'd already gone too far. Mk2 didn't fare well on the freedom of motion checks. It wouldn't rotate freely in either direction. The rod end joint kept binding. Just playing with the rod end joint, rotating the rod end a bit, and applying axial force at some points in the motion allowed full rotation in both directions, but nothing close to free rotation of the original branch engine, always requiring some coaxing. It did seem that it took a bit more rotational assistance for clockwise rotation, as well as some coaxing in both axial directions. The mechanism just seemed to prefer counterclockwise rotation. Maybe this directional sensitivity isn't surprising, since the mechanism isn't symmetrical. I found that the mechanism was reasonably free with counterclockwise rotation and only an axial tweak toward the crank at the onset of the exhaust stroke. On a whim, I added a rubber band to provide this axial tweak. Lo and behold, it rotated in the counterclockwise direction without touching the rod end, but bound in the clockwise direction. With little hope, I applied air and gave it a spin. Initially, it took about 15 psi to get it running, but it did run. Concerned about the crude construction, it seemed worth checking the valve operation. 2 LEDs, red for inlet and blue for exhaust, provide reasonable visibility of the valve opening and closing, and the valves behave about as expected. It's worth noting that the valve port holes are fairly small diameter, and the frame port locations for Mark II are strange compared to the original Branch engine. This resulted from a combination of the asymmetry of Mark II, the variable crank offset during a stroke, and the seat-of-the-pants construction. Better valve port design could certainly provide some performance improvement, and this is a subject we'll discuss in detail in other videos using the engine simulation and variations of the baseline metal engine design. Since the initial Mark II build, the engine has been disassembled and reassembled several times, and its performance hasn't been terribly repeatable. But if anything, its performance has improved, probably from some running in. While initially wanted pressures on the order of 15 psi, it's now capable of self-starting and running at noticeably lower pressures, suggesting a reduction in friction losses over time. Frankly, this is better than I expected. Looking at its operation in slow motion, it's clear just how sloppy this thing is. The piston rotation is certainly a bit disconcerting, and everything sort of flops about. But this is certainly influenced by the makeshift substitute for a proper ball rod end bearing. With a hard connection to the wood workbench, it sounds like a car with flats running on railroad ties, but freeing it from the bench sounds better than it looks. At this point, it seemed reasonable to claim victory and not push my luck. A dynamometer test seemed a little foolish at this point, since just a light finger load on the small diameter crankshaft quickly stops it. The only thing that remains is to try to better understand the need for the rubber band. It's a little difficult to illustrate, but it seems that the net force along the crank pin — remember that the flywheel is driving the engine during the exhaust stroke when the rubber band is needed — is insufficient or even in the wrong direction to initiate rod end motion back toward the crank. Even if it were in the correct direction, it may be that the axial force component's angle to the crank pin is too large and there's an axial friction lockup condition. I've toyed with the idea of making a small metal version of this engine. Just playing around, there are an endless number of shapes that might be employed, and the goal might be to create a bit of a Salvador Dali-like appearance and something intentionally providing a machining challenge. I purchased a small ball-joint rod end to see if it might work. This one uses a PTFE bearing liner, but is very stiff, and the friction losses aren't encouraging. A metal-to-metal joint, possibly freed a bit with time-saver lapping compound, might be more suitable. A compression spring at the end of the crank pin, looking something like this, might be a substitute for the rubber band. There's still the question of whether an engine with much better fitting joints would work. Are those added degrees of freedom necessary for it to run? I don't know, but the CAD model suggests that this might not be a problem. Then again, the CAD model didn't predict the asymmetry of operation, the fact that Mark II will run only in the counterclockwise direction, nor the need for the rubber band. But a metal version is low on my to-do list, and probably won't happen. Any brave souls out there who'd like to give it a go? So, in summary, the original oscillator geometric constraints aren't mandatory for an engine to run. On the other hand, they certainly seem a good idea for an engine with any hope of running smoothly and doing useful work.